All right, so welcome back. This is another IR and NMR type structure determination problem. I haven't made one of these videos for a while, and I really like these types of problems. I think they're a lot of fun. So I'm going to go ahead and do one because that will be fun. So in this problem, we're given an NMR, and we're also given an IR spectrum. So a little peek at the IR. And basically, we're not told very much else, and we're asked to figure out what a plausible structure for this might be. And then we're given this other information about what the boiling point of this substance is. So that will help when we actually come up with a structure to sort of double check, does that sort of make sense for this problem. So let's go and get started. The first thing that I would do when I'm looking at an NMR first, and I'm definitely going to look at the NMR first because it's got a lot more information than the IR. But the IR definitely helps us with identifying some functional groups. So the NMR, the first thing that I'm going to do is just sort of go through and annotate and sort of pick out the things that are jumping out at me. And definitely this group over here, this 3-high triplet, and then this group, which is a 3-high doublet. That's the first bits that I would definitely consider. And a 3-high triplet is really common. We're going to see that sort of all the time. And the reason that it's really common is because the way that you get a 3-high triplet is from a methyl group that's bonded to a methylene linker. So, we're going to have 3 protons here in this CH3 group. It's going to be split into a triplet by a CH2 group. And it's pretty common to have these little ethyl groups sort of all over the place, right? So anytime you've got CH2 bonded to CH3, and that CH2 will be bonded to some other stuff, right? But that's very commonly gonna give you this type of peak here, down around 1 ppm. That's the chemical shift that we should expect. So very clearly we've got something like this. So already we're sort of figuring out little pieces of our molecule, right? We know that it has to have something that looks like this, and that's a piece of our puzzle. And then as we go through, we'll sort of figure out all the other little pieces to put it together. So I think it's sort of fun. Here we've got a 3-high doublet, and a 3-high doublet is actually something that's not as commonly seen. A 6-high doublet is really common for an isopropyl group, but a 3-high doublet is actually more rare for sure. But a 3-high doublet suggests something like this, where I've got a methyl group. So that would be my 3-high doublet. And then on the adjacent carbon, just got 1 hydrogen, right? That's how we get to this doublet, is that I've got an adjacent carbon with just 1 hydrogen. And then I've got other things, going off over here, maybe alcohol, hint, hint, or another carbon over here. It could be 2 carbon groups as well. But something like this is indicating that we've got this 3-high doublet. That's how we'd get there. So again, we've got another piece of our puzzle here. So we'll just sort of keep going through. This peak down here is a little bit messy. So I think I could convince myself that there's a broad peak in here, maybe, and then there's this like really complicated, forest of peaks in here. This is going to integrate to 3. So the integrations here, I guess we should talk about that real quick. So this peak over here, it's been set to integrate to 1. So that's whoever took this NMR, they set this peak equal to an integration of 1, and then these peaks are based off of that. So they're not going to be exactly 3, but they should be close, right? So they should be close. So 3.13, that's rounds to 3. 3.14, that rounds to 3. This is a pretty nice spectrum. So I think we can easily say that. Now here, this whole thing integrates to 3.3, 3.29. And I don't think that this is, just like one species. I think that there's a mixture of things going on here. If something integrated to 3 and it was just this like giant mess and it was just one type of chemical environment, that would be very strange. So to me, this is a mixture. Maybe we've got something in here that integrates to 2. Maybe we've got something that integrates to 1. We should be thinking about where is this methylene linker going to come. So probably this sort of mess right here is probably this methylene CH2. And then maybe I've got something else underneath here. So we're going to just not worry too much about that yet. Definitely, I guess I would be thinking this CH2 here probably is in this mixture here. And then maybe this proton here is this one over here, but obviously we'd have to have some other splitting happening, because if this was just being split by the CH3, it would be a quartet. This is more complicated than a quartet. It's actually 6 peaks in there, is what we can see. So this one, maybe I'm thinking over here. This one, maybe I'm thinking the CH2. I'm probably thinking the CH2. But at this point, we don't know too much more. So that would be the groundwork that I would lay for the NMR spectrum. And then I would say, let's look at the IR. And so when I looked at this IR, it's actually sort of funny because the first thing I did was sort of like laugh almost. This is an alcohol, right? Like this is just so obvious and really just a nice IR spectrum. And this is very clearly an OH alcohol stretch. It's not a carboxylic acid. A carboxylic acid would be broader. It also would not be absorbing as much as this OH, but this is just a beautiful OH stretch. So clearly that is a functional group that we're going to have in this molecule. And then the other thing that jumps out at me is that we've only got sp3 hybridized CH stretches. So right below 3,000 is sort of like a wall here, and then all of these are below 3,000. So very clearly, sp3CH is the only type of CH stretch that we have in our molecule. So, we don't need to worry about double bonds. We don't need to worry about, sp2 hybridized carbons with hydrogens on them. And then we also don't need to worry about anything in the carbonyl region. So 1680 to 1715, something like that, or 1700-ish, sort of a more narrow but also very strongly absorbing peak. That's where our carbonyl carbons would come. C double bond O stretch, that's where that would be. So we do not have that in this IR, but those are like the most common things you're going to look for in IR is, where's that C double bond O? How is it shifting? Is there conjugation? Whatever. But we definitely do not have that. This tells us we've only got sp3 hybridized carbon and hydrogen bonds, and then clearly an alcohol. So at this point, what I did when I was first looking at this is I said, okay, well, let's start putting these pieces together. And I'm just going to start by writing OH and then carbon. So I know that there's an alcohol, and then I just want to start putting the pieces together and sort of see where I end up with. So the first sort of go at this, you're just guessing, right? And then we want to guess it. You sort of want to guess and check, I guess. You want to check, you want to give it a go, and then check to see, does it make sense? Do I need to modify something? Does everything fit? Does everything not fit? So then I would just start with this piece. I would say, well, I know that I've got something that looks like this, so let's draw that in there, CH3. And then on the other side, I know that I've got this sort of ethyl group almost, so let's draw that in there. And then let's take a step back and see if it makes sense, right? See, does this molecule sort of fit what we're seeing here? Can we rationalize everything? Is there anything that's out of place? But if you go through, this seems like a good guess at this. So let's start at this end. So this would be this proton here. So let's label these A, B, C, D, E. So my B protons, I would call them, out here, it integrates to 1, and then it would have somewhat complex splitting. It would be split into a triplet by this CH2. It would be split into a quartet by this CH3. We're probably not going to see that as clearly, right? It's pretty complicated being split by 2 different environments, but I think it's very reasonable that's that signal there. This CH3 here, we already said that should be this one. This CH3 over here, that should be D. That makes sense, right? That all matches up, should work out. C is going to be in here. So this is integrating to 3.3. So we could definitely have those 2 protons sort of hidden in there. They're probably these taller peaks in there, but definitely could be C. And then E, so if sometimes you're not going to see these OH peaks because, if your solvent is protonated, if your solvent is water or something like that, then you're going to get exchange. But we could definitely have those OH peaks. That could be this broad hump here, getting a little bit of exchange. This could be solvent. It could be water. I'm not sure what the solvent we're using here is. But this to me just looks like a little impurity, so I'm not going to worry about this peak. It also integrates to less than 1. And I know that this is, that peak there. So I would guess that my OH is somewhere, maybe this broad thing in here as well. So I'll just put an E next to that. And that all makes sense, right? And then this structure, again, we've got an alcohol from our IR. We don't have any double bonds, only sp3 hybridized CH bonds. So this makes a lot of sense. So I'm pretty confident with this. I looked up what the boiling point of this 2-butanol is. And so 2-butanol has a boiling point, a literature boiling point of 99 degrees Celsius. So it's a little bit higher than this, but if you're measuring the boiling point, if this was like experimentally determined, not given, then that seems to fit. So yeah, so that's what I'd go for. Yeah, if you got any questions about this, let me know. If you got other examples you'd like me to talk through, definitely let me know. Hopefully that's helpful for someone. Cheers.